Hello from the Forcetronics YouTube channel, and welcome to how to design a backup power circuit using supercapacitors. And this is part 2 in a 2-part series. Before we dive into our design, I'll just mention, please support Forcetronics on Patreon, where you can find exclusive content, including exclusive content from this video series. If you haven't already, please subscribe to the Forcetronics YouTube channel. And if you like what you see here, please hit the thumbs up. All right, let's jump into our design and see it in action. All right, we spent a lot of time in part 1 going over the design in detail and reviewing the schematics. In part 2, we're going to see a demo of our working power backup circuit. We're going to do a little bit of a review of the PCB layout, and then we're going to do some tests, some measurements, and talk about some tips for implementing the circuit. And you can actually see the PCB there on the right without any parts on it. Now, I will mention, I said this in part 1, that I was doing this design before actually getting the PCBs made up and tested. So I did part 1 before I got the PCBs manufactured and tested. I did find a mistake, which at first I was bummed about, but I actually think it's better. I was able to fix the board, or at least hack into the board to correct the mistake. So we'll also in part 2 talk about the mistake and how it was fixed. And then, of course, all the files, the BOM, the Gerber files, the PCB design. The fixed version is going to be available once you see part 2 on Patreon. Okay, here is our design. This is the PCB you just saw in the picture, except this time it has parts on it. On the left here, this screw terminal is our load for the backup power. This screw terminal is the input for our main power. If you remember, we have an isolation circuit, and you could jumper around the isolation circuit if you didn't want to use it. You can see I don't have the jumper on. And you can actually see I have a strange wire here connecting to a pin to the isolation circuit. So I'll explain that. That was the mistake. So I was able to fix it, and we'll talk about that after this video. Here is U1. This is the max chip that does all the work. It serves as the boost regulator for the backup power and then does a buck regulator to charge our supercap. Here is our supercap right here. If you remember, we're using an 180 farad supercap, and we didn't really need all that capacity. We only needed about 45 or 50 farads from our calculation in part 1, but supercaps, the lower their capacity, the less max current they can deliver. So we had to go with a higher rated capacitor to deliver the current we needed. All right, these pins over here are control and status pins. So right now I have a connection that is enabling the backup power because I'm not using a microcontroller to do that. So I have another 5-volt line that just enables the backup power. Okay, you can see that we're powering my, if you watch my videos, the Forcetronics ESP32 dev board, which I have videos on. But what I'm doing is I'm just running some code that cycles through different colors for the RGB LED. So I have an external power supply serving as my main power source, right? So now I'm going to remove power. Pay attention to the LED. It won't be disturbed. So our code is not disturbed. Our circuit's not disturbed because the backup power kicked in. So first thing I'm going to do is measure the backup power with my voltmeter. If you remember, in part 1, we set that backup power voltage to be 4.85 volts. You can see we're almost right on there. So we got the right voltage level for our backup power. Now I'm going to verify that our cutoff circuit worked. And our cutoff circuit did work because we don't see the backup power at the main power port. Of course, I had to do a little hack to make that work, but we'll see that after this video. And then lastly, I'm going to measure the capacitor voltage, right? So this is before the regulator. What is the voltage at the capacitor? So we can see it's almost 4 volts and it's slowly dropping, right? Okay, so now I'm going to return the power, the main power, and we can see it's not drawing any current, right? 0 amps. That's because the isolation circuit is still kicked in. To turn off the isolation circuit, I actually have to turn off my enable power. So when I do that, we can see that the main power now is powering our circuit and our isolation circuit is acting like a short. And if you remember, it was 50 millivolts. We're drawing much more than that because the main power is charging the capacitor back up. All right, let's look at the schematic fix we had to do. Okay, here's our backup power schematic, which we covered in detail in part 1. Let's talk about the change we had to make. Q2 is our P-channel MOSFET, which serves as a switch to isolate our 5-volt main power from our backup power bus. When we have 5 volts applied, this acts like a short and the two buses are combined. When the 5 volts disappears, the main power, this acts like an open. And so the mistake I made in part 1 is I tied this directly to the gate of Q1, which is an N-channel MOSFET, which I'm using to turn on and off the P-channel MOSFET. And what I figured was, oh, if main power goes away, this will drop, the gate will get pulled down, this will turn off or act like an open, and Q2 in turn will turn off. Well, the dumb thing I realized, and you always realize this after you make the mistake, is, hey, if this 5 volts drops, the backup power kicks in. So it never gets below the threshold of this, the gate, the source voltage to shut this Q1 off because our backup power kicks in and keeps Q1 on and therefore keeps Q2 on. So I realized this when I first did my testing. So I said, you know what I can do? I can tie it to the BKB pin. This is a status pin on the regulator that is an active low when we're in backup power mode, but is pulled up to a high when we're in main power mode. So with main power applied, BKB turns on this MOSFET, acts like a short, turns on this P-channel MOSFET, acts like a short. Once power disappears and the regulator starts sourcing power from the supercap, BKB goes low, which then turns off Q1 and in turn turns off Q2. So that's how I did the fix. And what I had to do is I had to take an X-Acto knife, cut my trace that went to the main power into this gate. And then I used that wire to go from BKB to the gate, or actually to R11. The only other change I made is the pull-up resistor was 1 meg. I lowered it to 10K so we don't get too much of a voltage divider with this pull-down R11 resistor, and we get enough voltage to make sure that this turns on correctly. Okay, let's look at the layout. Okay, here is the layout for our backup circuit. The red traces and parts are on the top. This is a 2-layer board, so we have a top and bottom. The blue is on the bottom, and these green pieces connect between both layers. So here's our control and status pins. Here is our connections for our screw terminals. And then these are vias to make certain connections, and all of our parts are on the top, right? So if I turn on my ground planes and my power planes, we can see they get filled in, right? So a lot of this red is the ground plane, but then I also made some planes for the high current areas near the regulator. What's important in this PCB layout is really how you do the layout around the regulator, right? So what is a regulator? This is a switching regulator. So it's using high-powered pulse width modulation to either boost or buck a DC value to another DC value, right? And this regulator does both. So one of the important things when you're working with switching regulators is having your bypass capacitors, and this one has a lot, right? So we have 247 microfarad caps, 222 microfarad caps, and a 1 microfarad cap. And why did I use those values? Because that's what the data sheet for the regulator recommended. So I have them right close to the output power or input charging pins, right? And we have these nice wide traces. Why? Because we have them close to the pin with nice wide traces because we want to reduce parasitic resistance and parasitic inductance in the traces so that this regulator works properly. And similar here with the inductor and the cap that goes against the supercaps, right? So the supercaps are down here. We're only using 1 in our diagram, but I put a footprint for a second. Here's our 22 microfarad, and here is our inductor. The other reason you want to have the inductors and bypass caps close to the regulator is because of EMI. So what happens is these high-powered switching pulse width modulated signals create harmonics which can be radiated from the traces and create EMI, which if you're trying to bring a device to market, there are certain restrictions on EMI. So having the capacitors and inductors close to the chip reduces the amount of trace area that these high-powered switching signals can flow on. So that means they act less like an antenna. If you have the inductor far away from the regulator, that trace acts like more of an antenna and radiates that EMI. So that's why it's important to have these parts close to the regulator and nice fat traces. Another thing I do is I isolate the grounds. So if you notice, there's sort of a cutout that goes all the way around here and is only joined right here. my bypass caps, my inductors, anywhere where the switching frequency is going, I connect to a ground plane I call PE, or power ground. And the idea is we want to keep that noisy ground away from our main ground to reduce its effect on sensitive components like ADCs or DACs or high-speed digital signals. We don't really have that on this board, but it's always a good practice. Let's look at our circuit again in action. We'll make some measurements. We'll see it with a full load, and I'll talk about some tips if you want to implement this yourself. Okay, here we are back at our circuit. The only difference here is now instead of the ESP32 dev board made by Forcetronics, we have load resistors kludged together. So I took some higher power resistors, I kludged them together, some in series, some in parallel. But basically this load allows us to get like 660 milliamps, right? So I designed this to be able to get a max continuous current of 600 milliamps for 90 seconds, right? So now I want to make sure I can get that and even get more than that with some margin and make sure it lasts with plenty of time, which it should because this cap is bigger than I need it to be. So we're going to see the main power, and right now it's supplying current to our load. There's our cap voltage, so that's the cap like almost fully charged. There's our main voltage. As you can see, we're pulling a lot more current, 660 milliamps. I unplug it, the backup power kicks in. Now notice, compared to the first demo, the voltage on the capacitor, right? We're measuring the voltage of the capacitor. This is not the backup power voltage. This is the voltage of the capacitor before it's boosted by the regulator. And you can see it's falling much quicker because we have a much heavier current load. Okay, now I'm going to move the DMM to the actual load so we can see the backup power voltage. So there it is. Notice it's a little bit smaller than what we saw in the first demo. And actually, as the capacitor drains, this voltage will drop a little further too, to about 4.8. So something to keep in mind with heavier loads, the voltage sort of sags a bit. Some of this might be IR loss, but I think over time, as the capacitor gets lower in voltage, this voltage slowly drops a bit, but it's not a big deal. Okay, let's look at some of the measurements we made and some tips on implementing this circuit. Okay, so the first bullet basically shows something I already said during the video, but I ran basically that same setup you saw for 3.5 minutes, and we were getting above 650 milliamps. So plenty of time. Remember, the goal for my circuit was 90 seconds at 600 milliamps. So we more than doubled that, and we doubled that because I had to use a high value capacitor, right? And you may not need these same voltage, time, or current levels, but we talked about in part 1 how to tune it for your needs. Another thing to keep in mind is once the capacitor voltage gets low, it drops quick. So one thing to realize about boost regulators is as the input voltage gets smaller, the boost regulator becomes less efficient. And if you look at a boost regulator's data sheet, you can see it. They'll typically have a curve showing efficiency versus input voltage. Keep that in mind. So it's going to drain power out faster because it's not as efficient. Also, as the capacitor's voltage drops, you still have to give the same amount of power. So as the capacitor voltage drops, the boost regulator needs to pull more current from the capacitor. So those two things combined, when I got down to about 2 volts, it was literally a couple seconds from when it went from 2 volts to 1 volt. And then once it was at 1 volt, if you remember from part 1, that's how we configured our regulator to shut off, right? To stop supplying backup power. What I will say is once it hit that 1 volt level, it did bounce a bit, meaning it dropped, shut off, the charge recovered a bit, it turned on again, and this happened in a matter of seconds. And then finally it settled and shut off. Keep in mind, my circuit has plenty of margin. And all I'm saying is make sure your circuit has plenty of margin because you don't want to be pulling much power when you get close to 1 volt. Another thing to mention is R6 and R7. I should have pointed out when we were looking at the schematic, but R6 and R7 were high-value resistors that we used to set that 4.85 volts on the output of the power backup circuit. So these resistors are important. They connect to a pin called FBS, and so the idea is they regulate the voltage at 4.85 volts when backup power kicks in. But they also tell us if main power is there, right? And if main power is high enough to charge the capacitor, and if main power gets too low to kick in backup power. One thing I'll point out is if you measure them with a voltmeter, you're looking for about 1.2 volts. And if it's higher than that, then it means you have main power. If it drops below that, that tells the regulator to kick in backup power. Well, when I first measured it with my voltmeter, backup power accidentally kicked in. And then I realized why that happened. These are mega ohm resistors, right? And my voltmeter has a 10 mega ohm input impedance. So I actually was loading down that voltage divider when I tried to measure it. So just keep that in mind. You can't really measure that FBS pin without loading it down a little. Another thing to be aware of is IR drop, right? So IR drop is if you have current flowing through, a signal path that has resistance, you're going to get voltage drop. Well, when you do this design, you want to make sure you have your backup power and 5-volt power close to each other. Because what happens is if the load changes on your 5-volt power supply, that voltage will vary a little bit at the backup power regulator, and that could cause it to stop charging. It could also cause it to provide backup power when you don't want it. So if you saw in my demo, I was using a power supply that went through some wires. I actually had to adjust my power supply a little higher than 5 volts to prevent this from happening, right? So let's say you have 1 amp coming from your 5-volt power supply. If you have 0.2 ohms of resistance there, you're going to get 200 millivolt drop, which means when you're at the regulator, that's only 4.8 volts. That's lower than the backup power voltage setting. So you can see how this IR drop can cause issues. So try to have your main power close to your backup power. Or if you can't do that, you need to have your backup power voltage setting low so that it doesn't accidentally trigger. And keep in mind, your MOSFET's cutoff circuit, that's going to have some resistance too. So keep that in mind. That's the main thing you might have to do is tune R6 and R7 a bit for your design. Okay, that's it for this video. If you have any questions, please use the comment section below. If there's anything you think I missed, also use the comment section below, and you can access the design files on Patreon. Thank you for watching.